A new seven-dimensional theory could solve the black hole information paradox.
One of the greatest enigmas of modern physics, known as the black hole information paradox, may be close to being solved.
New theoretical research suggests that black holes never completely disappear, which would preserve quantum information and even help explain the origin of the mass of fundamental particles. In the 1970s, physicist Stephen Hawking demonstrated that black holes are not entirely black. They emit weak radiation that, over an immense amount of time, causes them to lose energy and evaporate. This process creates a serious problem. According to quantum mechanics, information cannot be destroyed. However, if a black hole evaporates completely, everything that fell into it, including its quantum information, seems to disappear forever, violating a fundamental principle of physics. Now, a team led by Richard Pinčák proposes a solution based on a more complex view of space. In a study published in the journal General Relativity and Gravitation, researchers worked with the Einstein-Cartan theory in 7 dimensions, using a mathematical framework called a G2 manifold with torsion. Unlike common general relativity, which describes spacetime only as curving, this approach allows spacetime to also twist. This twisting generates a repulsive force at extreme densities, close to the Planck scale. Instead of the black hole collapsing and evaporating, the force prevents the process from ending. The result is a stable remnant, a tiny remnant with an estimated mass of about 9 × 10 superscript 1 kg. This remnant would act as a memory archive. Information would be stored in the vibrations, quasi-normal modes, of the torsion field within it. A black hole with the mass of the Sun, for example, could store an enormous number of qubits, enough to resolve the paradox.
Furthermore, the theory offers an elegant explanation for another major problem, the mass of particles. By reducing the 7 dimensions to the 4 we observe, the electroweak scale, approximately 246 GeV, naturally emerges, linked to the Higgs field, responsible for giving mass to elementary particles. In other words, the same geometric mechanism that safeguards information in black holes may also explain why particles have mass. The extra dimensions would be difficult to detect because the particles associated with them would have extremely high masses, far beyond what the Large Hadron Collider, LHC, can achieve. However, the theory makes testable predictions. These remnants of black holes could contribute to the dark matter of the universe. And traces of 7-dimensional geometry may appear in the cosmic microwave background or in primordial gravitational waves. This approach does not need to rewrite quantum mechanics. Instead, it suggests that the solution lies in a deeper structure of reality, with 7 dimensions. This is a promising idea that unites black holes, quantum information, and the Higgs boson in a single elegant geometric framework.